I'm Andy Kummel, and would like to talk today about novel routes to ALD of crystalline materials at low temperature, and very specifically aluminum nitride. And this is the work of two great students, Scott Ueda and Aaron McLeod. And this is primarily funded by the SRC Ascent Jump program, but we've also had funding from Research, who generously supplied us with the Hydrazine. And aluminum nitride is a material of great interest as a heat spreader. And that's because it has about the same thermal conductivity as copper, but it's an insulator, which makes it much more useful for microelectronics. And this plot over here is from the group of Eric Popp, and it shows some of the challenges. So this is the thermal conductivity versus thickness, and bulk aluminum nitride has a thermal conductivity of about 300. And there's two challenges, I should say. One is, as the films get less than about a micron, the thermal conductivity drops precipitously. So we can see over here, even in the ideal case, it's about 100 when it's only 100 nanometers in thickness. Now, the other problem is defects, which is the material conducts by phonons. And if you have defects, the phonons scatter and the thermal conductivity drops. So you can see over here, if you have 10 to the 20th defects, all of a sudden, again, your thermal conductivity drops down to 100. So the real challenge is to be able to grow aluminum nitride with low defects. And the defects can be oxygen or they can be grain boundaries. And I'll show over here these two gold stars is what we've been able to do, which seems to be the record thermal conductivity for materials of about 100 to 200 nanometers. Now, this is the typical structure one might have, is one could have a silicon substrate, and one wants to deposit aluminum nitride of about anywhere from 300 to 1 microns for a heat spreader. And normally what it is when you put this on silicon, you get a very poor grain structure. And what we've done is we've developed a technique to deposit a highly crystalline 25 nanometers by a technique called atomic layer annealing. And once we put down this crystalline layer over here, we can grow the rest of the material by sputtering, which is an inexpensive and fast technique. So we really are focusing our atomic layer annealed aluminum nitride, which gives us a large grain template to really improve the sputtered aluminum nitride. And this is shown over here, which is we have a structure where we put down about 23 nanometers of this crystalline template by atomic layer annealing of aluminum nitride. We sputtered on top aluminum nitride, and over here in the TEM, I'll show you that we are able to get these beautiful large grains. And we know from the XRD, the grain size is about 26 nanometers, which is a record for any aluminum nitride film grown on silicon by any technique. Now, these are the two primary applications that we're looking at. In logic, you may have hotspots on the wafer due to various devices that are highly active. And our goal would be to take the wafer, deposit on it a thin layer of aluminum nitride by atomic layer annealing, and then do the fast sputtering over here. And then the idea would be is the heat would be dissipated by first efficiently moving vertically through these layers and then spreading laterally. And one of the reasons we need this crystalline layer here is that we need the heat first to spread vertically before it spreads laterally. And whenever you have an amorphous material, you lose about a factor of 100 in thermal conductivity. And that's why we really want to have a crystalline layer all the way down to the hot spot. Now, the other application is for RF or micro LED. And in these applications, you actually dissipate the heat through the substrate. So the substrate could be silicon or silicon carbide. We put down our ALA layer. We then grow the thicker layer here by sputtering or by CVD. And then on top of that, we would grow the devices, which could be gallium nitride for RF or aluminum nitride, gallium nitride, indium gallium nitride for micro LED. And the idea here is by having the buffer layer made of high quality aluminum nitride, instead of the traditional gallium nitride, you gain in thermal conductivity so we can more efficiently sink the heat to the substrate. So this again is the paper by Eric Popp. And over here, this is the thermal conductivity in watts per meter Kelvin. This is the band gap over here. And you can see a lot of materials which have very nice band gaps like SiO2 and sapphire have very poor thermal conductivities. And these three are the big winners over here because they have reasonable band gap and they have high thermal conductivity. There's diamond, hexagonal boron nitride, and aluminum nitride. Diamond's a great material, but it's very hard to grow at 400 degrees Celsius or any low temperature. And hexagonal boron nitride only thermally conducts in the lateral direction. So this is the thermal conductivity of boron nitride in the lateral direction. You lose about a factor of 100 in the vertical direction, and that makes it much less useful. So aluminum nitride is sort of the material of interest for something you might be able to grow at low temperature. And this is this diagram again that I showed before. And I just want to point out the white dots over here are for amorphous films. All the rest of these are polycrystalline. And so our goal is really to grow a near crystalline material that has a defect density of around 10 to the 19th, so we can at least approach the theoretical limit. Now, we're going to use a technique to do this called atomic layer annealing. And this technique was invented by Professor Chen of National Taiwan University. And in this technique, the idea is that we use a third pulse in our ALD cycle to induce crystallinity. So over here, he did this on a lattice match substrate, sapphire. And what he did is he brought in a pulse of TMA, he purged, he brought in a pulse of nitrogen plasma, he purged, and then he brought in his argon pulse over here. And what's shown over here is when he does this atomic layer annealing technique over here, he can get a very, very sharp XRD peak compared to in red when he doesn't use the ions at all. And the other thing to take a look at over here is the TEM, and we see the sapphire, we see the aluminum nitride, and we can see that even on a lattice match substrate, we're only able to get grains, even with this technique, of about 10 nanometers. And for heat spreaders, we want to do a bit better than this. And I'll explain how we've modified this so we can do better even on a non-lattice match substrate, such as silicon. And this is the machine we use for this. So in our machine, what it is we have a plasma ALD tool over here so we can do the atomic layer annealing. And what's different is we want to do this at high temperature. So we use a high temperature precursor, which is the TDMAA, that we compare it to TMA. And we want to avoid the use of nitrogen plasma because we hope to be able to transfer this to use on large area wafers. So as a nitrogen source, we use the hydrazine. And in addition, we are able to bias our stage so we can control independently the flux of the ions from the energy of the ions. And then after we put down our template, we can either transfer directly into our XPS to look at the composition of our film, or we can transfer over to our ultra-high vacuum sputter tool so that we can put the sputtered material directly on the template and take advantage of the large grain size. So the way we do this is we come in here with our aluminum precursor and we end up having some aluminum with some ligands on the surface. We bring in our nitrogen precursor, which is the hydrazine, and we get rid of all that carbon and we end up with a NH terminated film. And then we bring in our low energy argon ions to organize the film into large crystallites. And so I'm now going to show you the need to have this interlayer for stress relief for these sputtered films. And over here, if we have a silicon wafer and we want to just put down a heat spreader by sputtering, we can put down 75 nanometers, but we can put down 50 nanometers, but if we go to 75 nanometers, it cracks. So it turns out that what you can do is you can adjust your sputtering conditions to first put down an amorphous layer, say of 10 nanometers, And then you can get uncracked films of 190 nanometers, but 290 cracks. And then you can go 25 nanometers and get a half a micron, which is great. If you go more than that, it cracks. So the thickness of this stress relief layer determines how thick of a sputter layer you can put down. And you actually have the same problem even on silicon carbide, which is much more closely lattice matched. Now, the problem with doing this is a thermal barrier, this amorphous aluminum nitride, because the amorphous aluminum nitride has a thermal conductivity of about 1 watt per meter Kelvin. But this at least shows us the road to be able to grow these heat spreaders, which is we need this stress relief layer. And this is just showing what we did is we went in and made films with a stress relief layer. We made films without a stress relief layer. And then what we did is we did the XRD over here. And in the XRD, what it is we can look at the texture of the film, meaning does it grow 002 or 200? And then we can analyze the width of these peaks to determine the size of our grains. So what you can see over here is if we grow on silicon carbide, we get grains of about 15 nanometers over here, which is pretty good. But when we grow on silicon, we need this amorphous interlayer over here. And our grain size, you can see, is not terrific. Depending upon which peak you look at, it averages out to being about 7 nanometers over here. And even on the silicon carbide, it's not huge. It's not huge. And so this was good. And then what we did is we had these films characterized by Eric Pop's group. So what Eric Pop's group did is they took the films that we grew with this thin amorphous layer over here, which is a thermal barrier, and they characterized the vertical thermal conductivity. And when they characterized the vertical conductivity, they saw that our 200 nanometer film had a thermal conductivity of about 70. So I put the data points over here, and you can see we're doing very well. But this is with a film that actually has very, very small grain sizes of about 7 nanometers and has this amorphous interlayer here. So we want to be able to do better than this. And so that's where the atomic layer annealing is needed, is to replace this amorphous layer with a crystalline layer so we don't have a thermal barrier to our substrate and we can have larger grains and lower defects here, because we'd like to move from here where we're about half of the theoretical limit to being much closer to the theoretical limit. And so what I'm going to show you is we were able to do this using the atomic layer annealing process at high temperature, using the high temperature precursor along with the hydrazine. So what we were able to do is replace that amorphous stress relief layer with this crystalline stress relief layer. And we're able to grow on top of that either 300 or 500 nanometers of our very fast deposited sputter film. And this is the XRD over here. And as you'll see in a minute, we're able to grow materials which have very, very thin XRD peaks, meaning that over here, this is very, very large grain sizes. So this was our first experiments that we had done with the atomic layer annealing. And we first started off using TMA and hydrazine at low temperature. And by low temperature, we chose 225 degrees. So in the XPS, we start off on a silicon substrate. So as I said, Professor Chen used sapphire, but we wanted this for use in silicon electronics, so we used a silicon substrate. And over here, we didn't bother to do anything more than a simple wet clean. So there's a little bit of carbon on the surface, a little bit of oxygen, mostly silicon. And this is 300 cycles over here. When we do this, we have about 3% oxygen on the surface. We did a post-deposition anneal, and that didn't do us much good. When we did this with low-energy argon ions. These were about 25 EV. And we can see a small XRD peak. And this corresponds, this small peak, to a crystallite size of 17 nanometers. But the problem is you can see this peak over here is barely above background. That means the film is a mixture of amorphous and crystalline, And when we look at the density of the film, it's much below the theoretical limit for crystalline material, which is about 3.3. So it means that this material is a combination of crystalline and amorphous, and this is not very good for a heat spreader because we want a purely crystalline film. Well, the next step is that we decided to go to a high temperature precursor, and this high temperature precursor is tris-dimethyl amido aluminum, and this is the precursor over here. And this is a great precursor because you can use this at high temperature. So we repeated the same experiment. This is our hydrogen HF clean silicon over here. This was run at 350 degrees Celsius. You can see over here that when we put down about 100 cycles, we have about 4% oxygen on the surface, and if we do 550 cycles, we get more. But this is not sufficiently crystalline again. The density is slightly lower. So we decided to go to 400 degrees C and try the atomic layer annealing. So if you look at this XRD and compare it to the next XRD, you can see this is night and day. So we went up to 400 degrees C using the same chemicals. This is our starting surface over here. And after 500 ALD cycles, we have 2% oxygen on the surface. And with these 25 EV argon ions in every pulse, this enables us to get to the theoretical limit for the density, which is 3.3. And then we can examine this primary peak here, which is the 200 peak. It has a full width at half max of 0.4, and this corresponds to a grain size of 24 nanometers. Now, this is really good because this is a grain size that's about 3 times what we saw in the sputtered films, and that means our grain boundary density is at least an order of magnitude lower. So our defect density is an order of magnitude lower, which is great for thermal conductivity. Now, this is a thin film, and what we want to do is use this film as a template for the sputtered film, and that's what we did next. Oh, I'm sorry, I have a comparison here, I forgot. So this over here was at low temperature with TMA and hydrazine. This is at high temperature with the TDMAA and hydrazine, and you can see that it's amazing how much just going to 400 C buys you in terms of crystalline quality. The density is theoretical, and the crystallite size is now quite large. Now, the next thing we wanted to do is to see if we were able to use this as a template. So over here, we put down just 25 nanometers and then sputtered on top this layer over here of aluminum nitride. And the XRD now reflects the crystallinity of the sputtered film. Over here, we did the same thing, but this is the amorphous film. And again, the XRD is going to reflect the properties of the sputtered film. And you can see this was transformative. By using the ALA, instead of having a grain size of 7 nanometers as seen by these very large wide peaks, we now have these skinny peaks over here that have a grain size of about 20 nanometers for the 2 dominant ones. And again, this increase in grain size of a factor of 3 reduces the defect density a factor of 10 for lateral heat transport. So we then wanted to see how well this scales. So these are not cracked films, and these are cracked films over here. And you can see with this 25 nanometers over here, this crystalline layer is every bit as good as a stress relief layer on silicon as the amorphous ones. And it also works on, we don't have the data here, but on silicon carbide. We did try the other technique in the literature, which is to add argon to the sputter gas, and that's known to work because you put compensating defects into your film. But this results in a very small grain size. These are the winners because we can deposit a half micron film with a large grain size. Now, this is a massive amount of data. We wanted to understand what is the range of conditions that work? So what we did is we looked at the ALA with 10-volt ions, 25 EV ions, and 40 EV ions for neon, argon, and krypton. And it works for all of them. You can see the sweet spot is about 25 EV for all three gases. For krypton, there's a much larger process range. But we really only get the extremely large grains for argon. So this process is not something that simply scales with the energy or momentum of the ions, probably because you also have the issue that the ions can embed in the film. And this seems to be the winner over here. And we're hoping to get a grant with a collaborator to do kinetic Monte Carlo to understand this for using other things. The 200, which I highlighted over here with the silver star, gives us 002, which is what we actually need for growing the RF devices, because that is the crystal orientation needed for RF and micro LED. We wanted to double check the effect of precursors. So what we did is this is at 225C, this is at 400C here. This is the thermal process, this is the ALA process. And you'll notice the ALA always gives us a factor of 2 lower oxygen over here. So at 400C over here, if we do this with TDMAA, 4% versus 2%, with TMA 7% versus 3%. So we gain a lot from the ALA in terms of oxygen content. And then what we wanted to do is also see the effect of temperature. And by going to higher temperature, you see again we can reduce the oxygen in the film. We also wanted to look at the effect of going between the two temperatures and the hydrazine versus the TMA on the crystallinity. You can see over here the thermal films never have as good crystallinity as the ALA films. And clearly the TDMAA at 400C is better than the TMA at 400C. And that's because TMA just undergoes pyrolysis at high temperatures, so you just get a very dirty film. This is clearly the winner over here. To understand the mechanism, we wanted to look in TEM. And over here in TEM, we first put down a 10 nanometer film using the TDMAA plus hydrazine with the argon at 25 EV. And this is on silicon. And what's very nice about this is the interlayer is only 2.5 nanometers. And as I mentioned, amorphous materials are terrible thermal conductors. So we want to get our crystalline aluminum nitride as close to the silicon as possible. If anything, we would want to have 0 of this. And when we come in, we can see over here our crystallites forming. And this is just a blow up of these regions. And we can see these crystallites are very, very close to the silicon. You can see the crystalline structure of the silicon, which is somewhat amazing that we're able to use the crystallinity of the silicon to help template the growth of the crystalline aluminum nitride. We then grew a thicker film. This is 40 nanometers over here. And the zone axes are different between the different crystallites. But when we look in over here again, we see these beautiful vertical grains growing like this. And I just showed the red lines to show the rows in the crystalline film because I know this is not the best resolution TEM image. But we don't, all the grains are crystalline and none of them are amorphous. And then what we did is we grew on top of a thin 25 nanometer film, the sputtered film. And so if you look here, you'll see these beautiful vertical grains. And I went through and drew the arrows in showing that the grains over here that we grew in the template layer actually continue on in the sputtered film. And this will be excellent for vertical thermal conductivity because there'll be no boundary between the ALA layer and the sputtered film because we're getting single crystallites going all the way from the ALA film up here. And then in the heat spreader, the larger the grains will help us for the lateral thermal conductivity. The last topic I wanted to talk about is how to measure the thermal conductivity and what we're doing for the future in this, because we've only measured vertical thermal conductivity. So normally what we do is in collaboration with Eric Pop's group, we put down a bar over here, and this bar is heated up to generate heat. And then we measure the heat spreading down to the substrate. Well, this works, but the problem you have is there's a thermal boundary resistance between the heater and the film. There's a thermal resistance in the film, and there's more thermal resistance between the film and over here the substrate, and then from the substrate you have thermal resistance itself. Now, this technique works as long as you're measuring a reasonably thick film, but in many applications we want to spread the heat a large distance, 100 microns, and what we need to do is measure the lateral thermal conductivity. And it turns out you can buy 25 micron thick glass, and if we do this, we can deposit the aluminum nitride on top and then lithographically deposit a heater and a thermometer so that we can measure the thermal conductivity in plane. And this is just showing the vertical technique that we used for the measurements I've already shown, where they bring in one color laser to heat, and then they bring in a second color laser to probe. And then this is the thermal conductivity that we're going to measure on these glass substrates over here so that we can have solid numbers for the thermal conductivity in the lateral direction. And the reason this works is glass has an awful thermal conductivity. So if you put down aluminum nitride and it has a conductivity of 100 and the glass has a conductivity of 1, you have about a 1-to-1 signal to noise ratio between the thermal conductivity in the layer of interest versus the substrate. And if you grow a micron, you finally have the really solid thing to make sure you really know your thermal conductivity is the thermal conductivity now in the aluminum nitride will be 6 times the thermal conductivity in the glass. And this is what we're working on now. So I hope I showed you that aluminum nitride, if you deposit it correctly, can have a thermal conductivity, even in thin films, pretty close over here to the theoretical limit from sputtering under ideal oxygen-free conditions, but we need to do better. And the way to do better is to have a crystalline template so that we have good thermal conductivity in the vertical direction, and we template the growth of larger grains so we can move these gold dots closer to the pink curve. And using the TD-MAA and Hydrazine at 400 C, we're able to grow grains of 26 nanometers, which is a record for grain size on silicon. And this can be used to grow this coherent grain all the way through our heat conduction layer. And I'd be very happy to answer any questions.
A couple of comments. Your oxygen levels are very impressive. They're lower than anything I've ever seen in a university reactor. If you remove that last little 2% that you have, do you think it could get you even closer to the theoretical limit?
So we think that 2% is mostly on the surface of the film, not in the bulk. So I think that we've seen some films that are as low as 1.5% or 1.3% oxygen. So I think the best way to get larger grains is just to raise the temperature to 450 degrees C, which was a suggestion from Jeff Spiegelman. And so we're having a new heater made by vacuum brazing, which can go up to 550 C.
If you were to be able to go to, say, 500 or 550 C, because now you're starting to get close to what they use in MOCVD, but you're still several hundred degrees lower. Do you think you can achieve the type of crystallinity without the argon bombardment if you were able to go to 550 or 600 C?
We do know that we've sometimes seen good crystallinity with the thermal ALD technique. So some samples seem to be highly crystalline, and we think that's because they're getting some of their crystallinity from the silicon substrate.
Can you elaborate a little bit more on the differences between, say, argon and krypton that you used to bombard the surface? Do you think it's a mass effect or some other effect?
Yeah, so normally for a given energy, smaller ions embed, which is not good for grain growth. So we were worried that the neon would never be any good because by the time the energy got high enough, it would embed. Then you have the problem when you go to krypton, you get more sputtering than with argon because the heavier the ion, the more sputtering you have. And that's a different type of disorder than embedding. So it seems the argon is the sweet spot, but we're beginning to learn more about how to control the plasma chemistry. So we're getting a spectrometer so we can actually look at the emission from the plasma, because it seems that the plasma power, independent of the ion current and independent of the ion energy, affects the quality of the film. And we don't quite understand that yet. So we're really trying to understand why the argon, when it's at a certain power, is giving us such great crystallinity, but we can't reproduce that even with krypton. But we don't really know right now.
Do you ever see cases where the power affects the growth rate of the film, where you might be removing part of the surface of the film?
Yes, we do. If we have the ion flux too high, we do see the growth rate gets lower.